Welcome to a new test and teardown video. This time it's a Sennheiser UPM 550. So it's a universal AC voltmeter, and it can handle from 10 Hertz to 1 megahertz or 10 Hertz to 100 kilohertz, different ranges. We got all sorts of filters built in, different standards, dBA, CCIA, IR, and the 1 kilohertz, different filter curves here. And then you can turn off the filter. You can have an external filter. It can be RMS or peak voltage. Tried to clean this a little bit. It was super slimy and dirty, but now it's sort of okay. Still quite rusty, and yeah, you can see, probably you can guess how it did look. You can see here the rust. It's very important how you store your equipment. The power on off here is not moving. I tried to move that a little bit. I expect it to be something like maybe that one. Yeah, but it's not moving. So I need to open it and inspect. The rear side here show a little bit about the different curves, the different standards. So if you select 1 kilohertz mode, it only detects the level at that frequency. You have, of course, the wideband mode and the different kind of stuff. So, and that will be the external filter mode. There's a little bit of calibration here for level, because there can be loss in your external filter, obviously. And here is a nice logo label. So I better open and inspect. What can we see here? The top is also, quite rusty. So you could expect the worst. So that is a little bit funny. So the 4 screws here at the back, and then I pull this up, and then it looks like, okay, I just pull the chassis up like that. Okay, pretty cool. That is a very brilliant way to build this instrument. Look at the different shielded rooms. We got a back plane down there. We got numbers written for all the different plug-in modules. That's probably different filters and stuff. The first one is, of course, a power supply. I will have to pull this up and investigate a little bit more than that. They are really different, the different filter units. And that will be the attenuator. That flat cable goes to a LED indicator board that handles all the different ranges like that. And you can easily unscrew here to service that panel as well. I mean, wow. And look at that. A thin circuit board for the switches to those LEDs. So there's no wires or no funny stuff going on there. This is a really good design. I am impressed. And there will be the external filter interface. Wow, top quality BNC connectors. Everything is impressively good done. And the bottom, look at that. A thick layer of varnish coating to prevent all sorts of corrosion and problems. And you see, here is some nasty water corrosion from the chassis that went in here. And it of course didn't not affect anything in here because it's nice and beautiful. That is how you do it. Yeah, I'll have to go and clean the on-off switch here. Yeah, this is totally stuck. Maybe we got some corrosion or some stuff in here. The way you change the different voltages is by moving the position of the fuses. A little mains filter, and the mains transformer is right there. All the rust. It's really nasty. So here is a little trick. Take some of this contact 61 kind of stuff here, right? So instead of spraying it all over the place, I just put some here, right? And then it normally goes a little bit easier than this. This is typical. This is the demo effect. If I didn't record this, you probably... okay, typical. Normally it goes a little bit easier. But it actually also clean rust away from chrome and from all sorts of stuff and make it nice and shiny again as well. I didn't fix it completely, but at least most of it is gone. Let's look a little bit on the different circuit boards. I pulled them all out for a deeper inspection, and this is the first one, the power supply. And you see, we got 3 sets of rectifier bridges, 3 sets of capacitors, and 3 sets of ZA723. That will be a temperature compensated linear regulator, and it's also capable of handling external transistors for much more current. And it can do current feedback and voltage feedback and both at the same time. So it's a very versatile regulator chip. And if you look a little bit closer on the date code, it says A018. And this is a little bit rare. Back in the 70s and 80s, you will find some brands using only 3 digits of date coding. So this 0 here is 1980. And the only way you can know that is by doing quite a lot of research. If you only got this board like this, but I have cheated a little bit because I got another board with another IC, and this one is from 1980. So that is why I know this 0 is 80. And yeah, it's a little bit funny to see the different transistors they're using here. See, a 135, and that will be an NPN. 136, that will be a PNP, and another PNP. And here, 139, that's another NPN with more or less the same gain, but I think this, yes, this is 80 volts, and everything else is 45 volts. So why not use 80 volts on both of those NPNs? I find this a little bit weird to have more different type numbers. You don't normally want to do that. All circuit boards, they are really, really nicely coated with a thick layer of varnish, and it looks a lot like it's been paint brushed. So that was the B16, the power supply. And yeah, I think we should just take these in a more or less random order. I was lucky to find the 15. Here's a little, I think this is a relay, and yes, a little op amp, and look at the date code here, 8029. So this one is from 1980. I got a little bit of normal transistors, tantalum capacitors, germanium diodes for signal rectification and all that kind of stuff. This is B12. Obviously, that will be all the different filters for the different filter bands you can select. So that will be bandpass filters with a little bit of adjustments. I really like the design here with trimmers adjustments going up. Of course, you can't manipulate the trimmers down here, so you need a riser board to be able to do that. They could probably have mounted those inductors sideways, but it will require quite a lot of different mechanical design. That one will be B13. I see a little, I think this is an optocoupler mode. I actually don't really know. And yeah, there's not a lot of funny things going on this board. And this is the last one, the option board. I think we got two different filters going on here, and you can select to mount the different filters, external or internal extra filters and stuff like that. And again, we got a little op amp here, and the plug-in board here is screwed really nicely to ground. Most of the power supplies, they of course go in parallel. We got some inputs and some outputs that is obviously not in parallel, so you can select the different signal path on the front panel. This one is a little bit interesting. It's called a B14. And here we got, let me swap this around. We got the AD536. This one is an RMS to a DC converter, handling quite a wide frequency range and signal level range as well. So it's a very interesting part. You also find these in a lot of multimeters and measurement equipment, not just stuff like this. Here is another very interesting resistor. It's called R455. If you look through the glass, you may be able to find a tiny little blob here. This is a temperature compensating NTC resistor, and it's a 1/4 millimeter tiny little drop. Here you can see it inside a little glass. So yeah, it's doing some sort of a temperature compensation stuff for the AC circuits. And again, trimmers accessible from the top. Really nice and fine. Earlier in the video, I explained a little bit about the power on-off switch. It was stuck. And see, now it's not stuck anymore. But I think during the cleaning process, or maybe it was already broken, I really don't know. But there's a tiny little holder mechanism that goes click-clack in out of a little holder thingy. And as you can see here, this is not holding anything at all, but it's moving nicely and freely. But I have a little hole here at the back where I can stick something through and then pull the switch in and leave it in so it's very visible. This was fixed in the on position. Then I can replace this on-off switch on a later point if and when everything here is okay, calibrated and super good and happy and cleaned and whatnot. But I will leave this switch permanently on for now. So that will be the first power on. and it is using 10 watts, and then it goes down. That is a little bit funny. We got only the power on LED here. Let's turn this off. Let's see if we can. Oh, we don't have any lights in any of the oh, that was weird. I didn't touch anything. What happened here? So that will be the filters, RMS mode. Okay, so all the, oh, and then it turns off. Test, okay, so this is test. So we've got a little bit of funny stuff going on with the filters. That will be, yeah, I kind of like this. It goes up and down like that. We got light in all the different ranges. So that will be 1 volt range, and we have no filter. We are in RMS mode. So let's try and see what happens if I give it a signal. We can give it a little bit of light here. So 1 kilohertz, 1 volt RMS is what I have, and then it goes plus 2 dB, and I think it has something to do with the loading. This one is in high impedance mode, and I think my generator expect a 600 ohm, or okay, I will go and get it correctly loaded. Hang on. So we turn off the filters, and we are in RMS mode. 1 volt, and I have now 1 volt RMS into 50 ohms, and here I have my through load. So that means my generator is correctly loaded, my cable is correctly loaded, and this one is a 1 mega ohm input. As far as I understand, there is no way I can change the different loading here on the inputs. It's a high impedance kind of machine, and it is exactly the same. So here is a funny thing that happens if I change between RMS and peak. Look at that, it is exactly the same that happens. So either the RMS board is not working, or yeah, it's much more important, the problem here. So I will test one more little thing before I try and poke around with the RMS features here. So let's go to the 1 kilohertz filter function, and let's try and change the input frequency. So if we look here at the back of the instrument, we've got this nice little curve here. I believe I have selected the 1 kilohertz mode, and that means at exactly 1 kilohertz it should not affect anything at all, right? But if I go just, I don't know if you can see this, but if I go just a little bit away from 1 kilohertz, my signal level should drop quite a lot. So let's try and test if this is really true. So let's go to 900 hertz, and here we go, 800, and then it's already more or less 700. Yeah, okay. So I think the filter here seems to be working, and we can go the other way as well. 1100, 12, 1300, and then the signal is gone again. So frequency wise, I mean that we select the right filters and all that kind of stuff, but there is a problem with peak or RMS. Obviously I don't want any of the filters connected while I play around with this. I think I got good news. So here's what I'm doing. I take a square wave 50% duty cycle, and I got a 2 volt peak. So that means the peak voltage is 1 volt. So now I am here in peak mode, and I believe the 1 volt should be right there, right? 0 dB is 1 volt peak. So that is how it should be. So if I go to RMS mode, look what happens here. it goes much higher. And that is, of course, correct because it's a square wave. It contains a lot more energy in RMS mode compared to the square wave. So that means the RMS detector is working, and all I have to do now is calibrate it. And I believe it's the potentiometers I can find here at the top. I will have to play a little bit with that and see if I am lucky. Otherwise, I'm probably gonna screw it up big time. Or I will maybe take some close-up pictures of the trimmers before I get started here. In my many attempts to try and calibrate this unit, I mean, I am now forced to take up the input attenuator stage. And here I find no trimmers whatsoever. I think the resistors we see here, that will be the different ranges or something like that. We've got a little bit of amplifier here. That shielded cable is the input, and it goes around some resistors and capacitors and what not. I'm trying to clean away all the spray from the contacts. I had to clean the contacts that were going really weird. There was a weird feeling when I moved them. So that will be the LED range indicator. Quite nicely done. And see this hole? So you can put this over the shaft. So after I've been through the super cleaning here of the attenuator and all that stuff, I didn't find any kinds of components not being correct here on the input board. So I've been through all the trimmers in this unit, and there's nothing that affects both of the levels, the peak and the RMS potentiometers. They're here and here, and of course I can trim them individually, but I cannot make. I mean, it's okay. I'll show you. So here is the one volt range, and I got one RMS in. See, I need to have it all the way down here, and I cannot get all that way. So this is the trimmer range, and this one must of course be in the center position, like that. And if I go to the peak again, see, I can't go all the way down. So I want to put both of these in the middle, and then I want to trim down the input, because this is a thing that goes on and on in all the different ranges. So there's just something wrong somewhere, and I don't have the schematic. So I was thinking about adding a little attenuator on the inside here, because it's a 1 mega ohm input. So it should be fairly easy to attenuate this about 2 dB. So let's see what I've done. This is now 1 volt RMS sine wave, 1 kilohertz, and it reads 0. And it's of course in RMS mode here, and I turned off the filter. Okay, so it's supposed to do 10 hertz to 100 kilohertz. So let's try and experiment a little bit with the frequency range. So this was 1 kilohertz, so let's take 100 hertz, and it goes tiny little bit up. Okay, so let's go 10 hertz, and it is still absolutely there. Okay, so let's go 10 kilohertz, half a dB down. Okay, let's go 100 kilohertz, and it's back. So this unit is now flat within a half a dB. I mean, this is probably back to, you know, original specifications. I don't know how flat it is really supposed to be. And let me show you a fun fact. If I go back to 1 kilohertz, let's go back to waveforms square wave. Obviously, it's hammering like that, right? This is normal. Let me dial down the level until we have 0, like that. Okay, we're now in RMS. So what's going to happen when I go into peak mode? It should have been -3. It's very, very, very close. And if I change the relationships here, then there is a lot of stuff that is not working. So I think I will just leave it as it is. I mean, we are again a half a dB off. So I think I have restored this unit. There's just a tiny little thing about input impedance, and I could have spent a few more hours working with the input circuit. I will show. Oh, come on, man! I will show you what I've done. Also, for frequency compensation, the two trimmers right here, they handle frequency compensation in 2 different points, 2 different frequency ranges. And my tiny little attenuator here is just made with 1 resistor and a parallel capacitor to compensate for the frequency. And yeah, this fixed my little problem. And I think I will just leave it as it is. I don't really care about my input impedance. It's a tiny, tiny little bit higher. So I want to say thank you very much for watching. I once again made a good oldie work a little bit again.